Okay, here we want to evaluate a surface integral of this form. We want to evaluate a surface integral, and here's the thing about this particular problem. We have a closed region. So notice this region I've got represented here graphically. We've got it bounded up top by z equals 4 minus x. And then we've got bounded on the bottom and on the sides. So really, with this particular surface integral, we have more than one surface. We have the surface, z equals 4 minus x, and then we have these little partial planes off to the side, on the bottom, on the back over here, and on the sides. So it looks like we have 5 surfaces to consider. So if we're going to evaluate the surface integral, we're going to have to consider each one of these sides. So here's what I need to do. I need to just go about this and address each one of these sides. Now, first of all, now remember what we're doing. We're looking, in each case, we're looking for normal vectors going outward, away from the interior of this closed surface. So here's what we might want to do. We might want to start saying, okay, well, let's consider the surface here on the bottom, on the xy plane. In other words, let's consider the surface where z is equal to 0. Now, if z is equal to 0, and we want the normal vector that's going away from that surface, well, we don't have to think much about that. That would just be, the normal vector would just be this. It would be negative k. And that would be our normal vector. So if z equals 0, we need a vector that's going straight down, so that would be, it would look like that. And you can see that would be n equals negative k. Now, what we want to do is we want to immediately calculate f dot n for this particular n. Now, let's see what that is, and then we'll integrate it. So let's see what this is. When z equals 0, here's what we have. We have x and y, xy here. We have 0 in the middle part. That's, since z is equal to 0, I'm just going to put a 0 there for z. And then we have x plus y here. And I'm going to dot that with 0, 0, negative 1. Now, after we do that, then we're going to have to integrate it. We're going to have to set up our double integral. So let's see what this turns out to be. This is going to be, well, if we dot product this, the first term is going to be 0, second term 0, and then the third term, it looks like, is going to be minus x minus y. That just comes from the dot product of this. Now remember, this is when z is equal to 0. Okay? When z is equal to 0. So now here's what we've got to do. We're just going to set up this integral. We've got negative x minus y, like this. And now we've got to determine our bounds. And you can see that our bounds are pretty simple here. X goes from 0 to 4, and so does y. So it's going to be 0 to 4, 0 to 4, and that's dy dx. Order's not going to matter at all in this one. But if you work this out, just integrating the way you would normally, what you're going to get is negative 64. And you can check that out if you just want to run through the integration and make sure it matches. Now, okay, so that's the first normal vector. I'll just call that n1. So n1 we get negative k. And to save time, I just didn't go through the integration here, but you know how to do that. Now, for the next one, remember we got 5 of these surfaces to consider. And each one we do this same way. This one we had n equals 0. Why don't the next one we let y equal 0? Now, and we will then consider the normal vector, the second one. So if y equals 0, you can kind of look at this. You can kind of look at this closed surface here, and you can see if y equals 0, and we're back here on this thing. Okay, if y equals 0, we're back here. Then the vector going away is going to point in the negative y direction. So it looks like this is going to be negative j. It's going to be negative j. So now we want to calculate f dot n2. So let's see what our f is now. Okay, so the f was xy. Well, if y is 0, this is 0. Then we have z. And then the last one, notice we have x plus y. So that's just going to be x. And we're going to dot that with 0, -1, 0. Now, if we do that, if we do that dot product, what we're going to get is just negative z. Okay? We get negative z, and now we have to integrate. So here we go. We're going to integrate this. I've just got a negative z in here, and now I have to choose my bounds. Okay? Now, in choosing these bounds, we just look and say, okay, we're just considering this surface over here where y is 0. And when you look up here, you say, okay, where y is 0, if we think about, well, what does z do? If we're just considering x and y, well, z goes, for any given x, it goes up here, starting at 0 to 4 minus x. Okay, so we've got 0 to 4 minus x. And then, so that's dz. And then what about x? Well, x goes from 0 to 4. So that's dx. Now, if we run through the integral on that one, if we go ahead and work it out, what we're going to get is 32/3. And once again, to save time, I'm just going to, these are worked out in advance, so I know we can do the double integral. So I'll just let you verify that if you like. And actually, I guess this would be negative 32/3. Okay, so now we have two surfaces out of the way. So let's see here. Now, while we're talking about the y's, let's go ahead and we've considered when y is 0. Well, let's consider when y is equal to 4, because that's a surface over here. That's this surface here. So let's consider this surface. So when y is equal to 4, and I'll call that, we'll talk about the normal 3. So here we go. Let's suppose y is equal to 4. Then we have the third vector, which is going to be just j. Remember, it's pointing away, so it's pointing in the j direction here. And then we could do the same thing as we've been doing. This is our practice to come and calculate the dot product. So this is going to be, now, things are going to be a little different now, because notice we've got xy, and y is equal to 4. So this is going to be 4x. The middle term is z, so that's just itself, z. And then we've got the last term is x plus y, so that's x plus 4. X plus 4. And we're dotting that with 0, 1, 0. Now, if we find this dot product, what we're going to get is only only z, okay? Only z. So then we can set up our integral again. We've got z, and now once again, z is going to go from 0 to 4 minus x, and x is going to go from 0 to 4. So I'll do dz dx. And this is going to be, if you work it out, 32/3. Okay, now we've considered 3 surfaces. It looks like we have a couple more to go. So let's look back at our graph here, our surface. Now we've considered 3 of these. Now something we haven't considered is when x is equal to 0. So when x is equal to 0, we are right back here on this little surface in the back. And remember, we're wanting a vector that goes away from the interior. So here's what we're going to do. So let's just look and see what this is. So now we've got z equals 0, and if z is equal to 0, then we've got n4 is equal to, let's see, you're going in the negative x, so I'm going to say that's negative I. Okay, so now let's do the dot. Now you can see this is kind of time consuming, but it's what we need to do if we want to find the surface integral. We got to consider every surface. So here we go. Now z is equal to, actually I said z is equal to 0 here. I think we're saying x is equal to 0. I'm sorry about that. So x is equal to 0. So if x is equal to 0, we go up here and we've got 0 for the first term and just y for the last. Okay, so we've got 0, z, and y. So let me just verify that. If we go back up, if I put a 0 in the first term, I get 0. Z stays the same. And then x is zeroed out in the last term, so we just get a y there. So it's, here we have 0, z, y. And we're dotting that with -1, 0, 0. Okay. Now, let's see what this is. It looks like, oh my goodness, it looks like that's just going to be 0. Well, if that's 0, then this integral, we could say from 0 to 4, from 0 to 4, 0, and then dA, or, let me go ahead and put this in. So we got dx, dy. Well, that's just going to be 0. Okay, so we've got 0 there. Now, let me, okay, so now we've got 4 surfaces, and now it looks like what we're ready for is we're ready for the 5th surface. And what we're going to say now is we're going to consider, looks like we've considered every surface. Now maybe we can consider this thing, this top part. I don't know if you can see that. Okay, we want to consider this top part. In other words, we want to consider, this thing, z equals 4 minus x. Now, what I'm going to do for that surface is, I'm going to do this, z equals 4 minus x. And I've got to compute the normal. And remember, the way we had been doing that, we had been saying, okay, well, I'm going to come up with this surface. I'm going to write the surface this way. I'm going to say z plus x minus 4. In other words, I use this notation. I just bring the 4 over and bring the x over, put everything on one side. And then what I want to do to get the normal vector is I'm going to find the gradient. So here it goes. I take the partial with respect to x, the partial with respect to y, and the partial with respect to z. Now let's go ahead and find the dot product. So I want to find the dot product. So I'm going to do this. I'm going to see what we've got here. We've got xy, that's the first term. And I'm just going to put z in there. Okay. We know that z is equal to 4 minus x. I'm just going to put z in there for right now, though. And then we've got x plus y. Okay, so x plus y. Okay, now, if I find the dot product, now notice every time we're doing the exact same thing. We're finding a normal vector, and we're dot producting it with the vector field, the gradient of the vector field. Okay. So, not the gradient of the, we're dot producting it. We're dot producting it with the vector field, not the gradient of the vector field. But now, here's what we get. We get xy plus x plus y. There's what we have. Now, that's what we've got to integrate. Okay, so I'm going to integrate xy plus x plus y. And now I just have to choose what I integrate first. I guess what I need to integrate first is, remember, if you look at the region up here, right? We're integrating this. So I think what I'm going to do first is integrate with respect to y. Okay. If you look down here, y goes from 0 to 4. And this is an easy one to set up the bounds because you have just a square region on the xy plane. And then I'll integrate with respect to x, 0 to 4. And when I do that, if you work it out, what you're going to get is 64. Actually, not 64, 128. Sorry about that. 128. Okay. Now, notice what we have here is we have 5 different numbers. Here's what we have so far. Now, we've addressed every surface. We've addressed all 5 of those surfaces. Now, let's take a minute and take note of what we have. First of all, we have negative 64. That's for our first one. Okay. Then we have negative 32 thirds. We have a positive 32 thirds. Then what do we have? Looks like we have a 0. Okay. And then we have 128. There's what we have. Okay. Now, let's see if we can remember what all those are. Okay. So we've addressed every surface, so we have to combine these. We have, was it negative 64? I think it was, negative 64. And then, let's see here. Get this out of here. Okay. We had negative 64, negative 32 thirds, and positive 32 thirds. We had 0, and then we had 128. And if we combine all of those, we get 64. So all of that work was what we did to integrate to find this. Okay. That's what we did in order to find that for this closed region. Okay. So we had this region here, this surface. Okay, so we had this surface that was closed. And we wanted all of our vectors to point outward. This is what was required for us to do that work. Now, let's see if we can get the same result maybe a little more simply. And that's what we're dealing with today. So let's suppose that I calculate this. I'm going to take the vector field, and what I'm going to get is I'm going to get the divergence. Okay? So I'm going to get the divergence of this vector field. Now, remember what the divergence is. The divergence is going to be, you take the partial with respect to the first part. Okay, so I'm going to, with respect to the x, the very first coordinate of that 3 coordinate, the I, j, and k. So if I take the derivative with respect to x, the partial with respect to x of the first part, I get a y. And then the partial with respect to y of the second part, I get a 0. And then a partial with respect to z of the last part, I get a 0. Now that's what the divergence is. And in a minute I'm going to summarize that. But just suffice it to say now we get a y when we do this. When we find the divergence of f, this is what we get. Now I'm going to integrate, first of all, with respect to z. Okay? I'm going to go from 0 to 4 minus x. And then I'm going to go with respect to, let's say, y from 0 to 4. And then with x from 0 to 4. Now to save time, I'll just let you integrate this. I know you can. But what you're going to get is you're going to get 64. Okay? Now, we got the same result with this method that we did from that lengthy method. Well, this is an illustration of the power of the divergence theorem. And that's the subject of this section. So, look, let's look at this. Let's just remember this, that when we talk about divergence, let's suppose we have a vector field. The divergence is the partial of the first part with respect to x plus the partial of the second part with respect to y. So you're taking the partial that corresponds with the coordinate, the x part, the part that we consider the x part, partial with respect to x, the partial with respect to y for the y. Now that's if you have 2 components there. If you have 3 components, then the partial of m with respect to x, the partial of n with respect to y, and the partial of p with respect to z. That's the divergence of a vector field. Now, this is the divergence theorem. Now, notice carefully. Let Q be a solid region bounded by a closed surface. Now, I think you intuitively know what a closed surface is. A closed surface is like a sphere, or like the thing we just looked at, oriented by a unit normal vector directed from Q. So it's directed outward. It's directed from the surface outward. If f is a vector field whose component functions have continuous first partial derivatives in Q, then this is true. Then you can evaluate the surface integral. This surface integral, you don't have to go through all the steps that we went through. And that can be painful. You can just do this. You can do a triple integral. And that's what we just did. This is the divergence theorem.